Yes, we can.
So good afternoon, everyone, and welcome to my PhD dissertation defense, which is entitled Power System Modeling, Calibration, and Cloud Applications using Modelica Language and FMI Standard. In this slide, there is an overview of the presentation. After an initial introduction, we have section 2, shows some examples of modeling of power systems components for a phase of domain studies using the Modelica language, and then their validation against the commercial proprietary tool that is PSSE. In section 3, we have the modeling approach used to represent power electronics components in Modelica, and they are validated against a tool called PSCAD, used for EMT studies. Section 4 shows the strategies for model library management with regression testing and continuous integration. Section 5 describes the steps taken to prepare and perform a plant model calibration in the cloud. And this is just a proof of concept for a cloud-based workflow to calibrate our systems models using real measurements. In section 6, there is another cloud application for power system analysis using synchrophasor measurements. And the workflow can be seen as another proof of concept for a cloud-based integration between data analysis and model-based analysis. And finally, conclusions. So let me start introducing this research work. Electric power systems are intrinsically very complex, and they include many different components. They need to be modeled for design, operation, and planning purposes. With more renewable energy sources connected to the grid and with the current electrification efforts, the complexity will continue to increase. So to help the players of the electric power system sector to perform studies and analysis, models and simulations techniques have been developed over time. We went from miniature physical prototypes to network analyzers and finally digital computer-based simulators. Dynamic simulation for electric power systems can be divided into two domains: electromechanical transients that started to be studied since the beginning of power system development due to issues about control and stability. And the time constants is around 1 millisecond or larger. The other domain is electromagnetic transients, and they started to be studied after the installation of the first high voltage direct current transmission lines, and the time constants in this case are around 1 microsecond or even smaller. So with more power electronics based devices that are connected to the grid, there is a need for EMT modeling and simulation for understanding the current power network and its evolution. In the past decades, several software tools have been developed to aid engineers in performing reliable studies. Nowadays, we have proprietary tools used by the industry, and they require the user to be an expert of their functionalities. The model equations need to fit the specific form of the numerical solver that is used by each tool. So it becomes quite inflexible when attempting to share models and data between tools. Another drawback is represented by the inconsistency of dynamic simulation results between different simulation platforms. So to overcome these issues and to remove ambiguity, the Modelica language, that is an equation-based, object-oriented language, has been proposed as a modeling tool for power system. This idea then led to the creation of OpenIPSL. The Modelica language facilitates the reuse of models among different Modelica compliant tools. And the models can be implemented separately without the need of a numerical solver. Modelica also facilitates the reuse of models by adopting the functional mockup interface standard, which allows models to be exported and imported as functional mockup units. In the beginning, the developers of the OpenIPSL library had little understanding about Modelica language, and there was no collaboration strategy. Group members worked in isolation, and different copies of the main library without version control were present. Model validation was conducted only once and just with a software-to-software comparison. So it was decided that an open source development strategy would be needed, and it should be based on up-to-date software engineering strategies. So the adopted solution should ensure both traceability and quality. It is particularly important to carry out systematic testing for component verification. So by adopting version control, the collaboration and development of the library can be carried out by independent parties at the same time. Code syntax verification was also added to the framework. So specific checks can be performed when a new update to the library is proposed. So this new workflow allowed the library to develop quickly. The validation of any model against the reference tool is very important to maintain the model quality and the confidence of model users. It is important also for power system industry to update models and their parameters, so they can reflect what is observed in the real world through the measurements. So keeping the models updated is a difficult task, requiring measurement data to be collected and processed, and then the validation of models against the measured data. In the recent year, different energy companies and utilities have invested in synchronized measurements, installing several PMUs, phase of measurement units. And some utilities have started adopting cloud-based platform for synchro-phase of measurement analysis. There is currently a lack of model-based analysis capabilities in the cloud-based platforms that is limiting the potential to use data to explain phenomena observed in the electrical grid with a physics-based perspective. The conventional power system tools in this task become a possible bottleneck, since they don't allow users to deploy the model's equations in modern cloud-based environments, limiting the entire model validation workflow. So in order to overcome this issue, the Modelica language can be used to create accurate power system models that can be exported via the FMI standard and deployed into cloud-based platforms. And simulations can also be performed using Python libraries. So the Modelica models can be deployed in the cloud and coupled with real synchro-phase of measurements, and can be used for model validation, calibration, and also for model-based analysis and diagnostics. So let's start with the modeling of phasor-based power system components using Modelica. The power system modeling enables analysis, design, and optimization of complex electrical networks. The mathematical representation of the components allows to simulate their behavior under different conditions with the aim of providing stability, reliability, and efficiency of the grids. In this section, particular features of the Modelica language are highlighted, showing the advantages of using a modern object-oriented language capable of describing dynamic behavior of electric components, with the results that are comparable to established commercial tools. The approach of modeling power system components in Modelica is described, and the basic example of electric power system network called a single machine infinite bus, that you can see here in this slide, is used. The system is used to model a power plant with, that we can see here on the left, with its controls connected to the rest of the grid through electrical lines and substations represented by buses. The small network represents a standardization to test different models implemented in Modelica, and then PSSE as a reference for our tasks. The plant that is analyzed is modeled through a generator connected to bus Gen 1 and its controls. In this case, we have the turbine and governor control loop highlighted here and the voltage control loop. The grid is represented by a generator connected to bus Gen 2, you see on the right. And between Gen 1 and Gen 2, we have other components like lines, a load, a three-phase fault to ground as well represented. The bus shunt is also used to connect other devices to this small network. So depending on the type of power system components that we want to model, the configuration of the generating unit connected to bus Gen 1, this one, can vary. The first category of power system components considered in this work is represented by turbine governors. They are important control devices in power systems that regulate the mechanical power output of generators Their main function is to respond to changes in electrical load and maintain system frequency within acceptable limits. An example is the model WEGOV here in this slide, Woodward Electric Hydro Governor model. It is an elaborated model, and as you can see on the left, we have the PSSE block diagrams. And the model is split in two parts. One up here representing the governor and hydraulic actuators, and at the bottom the turbine. Sorry, and here on the right, top right, the turbine dynamics, the component. The user-specific lookup table from Modelica language in the turbine model, that is specifically this one, allow to reproduce the nonlinear dynamic behavior of the component. The software-to-software validation of this component against PSSE has been performed with the single machine feed bus system introduced before, and with the WEGOV component in it. And the scenario considered in this case for the simulation is a fault applied at bus fault at 2 seconds and for 0.15 seconds. And here we have some plots showing the results. And it has also to be noted that the model has been run in several Modelica compliant tools, the same model. Next category.
Can I ask a question? So these turbine models already existed and you verified them by comparing the PSSE models, or you implemented these?
So I had considered the PSSE models as my reference, and I re-implemented them using the Modelica language.
Modelica, okay.
In order to show that we can get comparable results to the standard reference tool. The next category considered is the excitation systems. They have a critical role in maintaining stability and regulating voltage in the system. An example is this model DC4B. In this case, this is the PSSE block diagram and the corresponding Modelica block diagram. It has been highlighted the PID block because it presented some challenges. So to find the right dynamic behavior of this block, it has been necessary to check the state of its integrator with the output of the PID block. And during a dynamic simulation running PSSE of an SMI system that has the DC4B model in it. So here we have the output of those quantities that we wanted to check, the PID output and the state of the integrator of the PID block. And it can be seen that when the PID reaches its limits, then the state of the integrator freezes to avoid wind-up effects. And that led to this implementation at the bottom right. So to test that the approach was valid for this implementation, again, we considered an SMI test system, in this case with the DC4B model in it. The usual scenario with a fault 2 seconds for 0.15 seconds at bus fault. And here we have some comparisons with the quantities like generator terminal voltage here on the left and the states of the PID block to show that they are corresponding to the ones that we get from PSSE simulation. An alternative approach for the validation of this component is offered by Modelica. And it consists of simulating only the block represented from the DC4B exciter system, driven by external input signals that are collected from an SMAB reference in PSSE and saved into this table, lookup table. So the PID, in this case, model has been modified, as you can see here on the left. And the integrator block with the integrator block has been replaced with an input, so that we can use the integrator state trajectory instead. The new test system has been created then with just the target model and all the inputs that we have in the table. This is the block diagram representation of the test system, and the text layer representation shows how the inputs of the block are connected to the signals from the table. For the validation, the usual scenario with the fault at 2 seconds for 0.15 seconds of bus fault. And the results that are shown in this plot, they come from the simulation of the SMIB test system in PSSE. And this is the output of the excitation system. We have also the output of the same component from the SMIB implemented in Modelica, and the output of this block here that we see in this new test system, which you can see here all aligned.
So I have a quick, more comment than a question. So
yes,
you basically had to apply software re-engineering tactics in order to really figure out the implementation in PSSE and the other programs. And luckily you had access to internal programs.
Yes, so let's say, usually this is also described in another slide later. So usually the process consisted of, first of all, since we are considering PSSE as our reference, we took their manuals as our reference also to study the different components. When the info, let's say, was not enough to describe the whole dynamic behavior, then additional search in the literature was performed. And once we collected all the info and we could understand the dynamic behavior, then we proceeded with implementation in Modelica.
Okay, thank you.
Welcome. Another type of power system component considered is the power system stabilizer, PSS. They are crucial components in electric power systems that work to maintain stability, particularly during transient conditions. And in this example, we consider the model PSS2A. To understand the dynamic behavior of the ramp tracking filter, that is this block inside the whole PSS2A model, the continuous time trajectories of the states of this block were analyzed. And those trajectories were obtained from a simulation in PSSE of an SMIB test system with the PSS2A. The final implementation of the ramp tracking filter that you can see here on the right took advantage of some particular features of the language that are highlighted here in the slide. So in particular, the creation of arrays of transfer functions and the accessibility of any element of the array facilitated the implementation of this model that was then introduced into the full PSS2A model. You can see here at the bottom left. Another characteristic of the Modelica language that you can see in this slide is that we have the possibility to implement models in the traditional way with block diagrams, as this PSS2A model here, or with coding, like we did for the ramp tracking filter here. The software-to-software validation for this case with the usual SMIB test system has been performed with the scenario of the bus of the fault, three-phase fault applied at bus fault at 2 seconds for 0.15 seconds. And here we have some quantities plotted. Again, the Modelica model has been run in more than one Modelica compliant. And these are additional models that have been implemented during research work for the different categories. As we've seen in the previous slides, the additional value of implementing and validating models with the Modelica language is the portability of system models using validated components. And as an example, in this slide, we consider the IEEE 14 network model. It is more complex than the SMIB that we used in the previous slides. And also for the validation, we considered the scenario with the fault by the bus 4, 3 seconds for 0.01 seconds. And here we have an example of the voltage at bus 1 plotted together with PSSE plus all the other Modelica compliant tools where the model has been, the simulation is being run. So after illustrating the modeling of some power system components in the phasor domain, let's see examples regarding the electromagnetic transient domain. With the enhancement of power semiconductors, the application of power electronics has been extended from traditional domestic and industrial applications to electric power systems. And with time, the application areas of power electric converter systems for generation, transmission, and distribution of electric energy has been extended for several reasons, as we can see in the slide. The use of power electronic converters in power systems is also motivated by the need to improve the efficiency and reliability of the existing electric infrastructure for integrating renewable energy sources and storage systems. So the work of this section started considering the implementation of a basic building block that is called off-bridge converter with its two representations, the average model and the switching model. You can see how this is the basic block that can be used combined in parallel or series to have more complex representations. After the implementation of the basic block of the off-bridge converter, then the Modelica implementation of the average model of a three-phase static compensator called STATCOM has been carried out. So the work performed started from the model that was given in PSCAD that you can see in this slide. And that was analyzed to identify the different component subsystems before assembling the whole system. And this is the final representation. That is the result in Modelica. That is the result of performing implementation and validation against PSCAD of the different subsystems. To check, to perform the validation of the implemented model, we consider two scenarios. The first one is the operation mode with reactive power control. And this is the scenario illustrated in this slide, where you can see there is a step of the reactive power at 1 second from 0 to 125 megawatt. And in addition to that, there is also a three-phase fault ground applied at the bus where the STATCOM is connected to the grid, applied at 5 seconds for 0.75 seconds. Is there a question?
So how did you bring this Modelica models into PSCAD? How did you interface that?
So the idea was the same as with PSCAD. So what I did was to create a library of components from the analysis of this initial PSCAD model. I went down, let's say, to each subcomponents and subsystems to understand what we have already implemented and what we don't have. And then I performed the implementation of each subcomponents, validating it against PSCAD, and then assembling everything in the end to have the full system. So I created my own library in Modelica with the corresponding components that I identified in the PSCAD model here.
So at this time, like whatever the model you develop in Modelica, that can be bring into commercial software, PSCAD or PSSC. How many software? Ideally, it's all software, right?
Well, if I understood correctly the question, the procedure, let's say, to import this kind of models into the standard tools usually refers to the FMI standard. That means the models that we created in Modelica are exported as an FMU, and then the commercial tool should be compatible with that standard.
I see.
In order to import the model.
Okay, great. Thank you.
Welcome.
One quick question here. Your errors are really very small. Did you have to go to very small tolerances on the Modelica side or not?
Usually for the validations in general, I've used the tolerances like 1 to the power minus 6.
Okay. That is normal and right. Okay.
And I try to keep it, let's say, correspondent, of course, to the tolerance set in the commercial tools.
Yeah. Thank you.
You're welcome. So we were talking about the validation of this model. So after describing the step in the reactive power at 1 second and the presence of the three-phase fault at 5 seconds, we can see that after an initial variation here at the beginning of the reactive power injected by the STATCOM to reach an equilibrium point, the measured reactive power stays at 0 megawatt until when the step is set at 125 at 1 second. Then the reactive power injected by the STATCOM increases, trying to track the new reference value. Then we see here a drop that is due to the three-phase fault applied to the bus where the STATCOM is connected. Correspondingly, the voltage of the bus where the STATCOM is connected, after reaching the value of 1 per unit, has a step 1 second that is corresponding at when the STATCOM injects reactive power. And that is that means the device is trying to track the reference here in reactive power. Then we can see that it stays at more or less constant value until it has a drop due to the three-phase fault to ground by the device, and then it goes back. Once the fault is cleared, it goes back to previous value. The second scenario that has been considered for the validation is the operation mode in voltage control. And in this case, we can see the presence of a three-phase fault to ground applied at 5 seconds. So we have an initial oscillation of the reactive power injected by the STATCOM that is necessary to make the bus voltage reach 1 per unit. And then it stays at that value, and the reactive power is maintained at 0. Once the fault is applied at 5 seconds, the STATCOM reacts injecting reactive power. And we can see a small drop in the bus voltage. With the injection from the reactive power from the STATCOM, this is going to compensate the drop. So the voltage of the bus goes back to 1 per unit, as it is supposed to. Once the fault is clear, then the reactive power from the STATCOM drops to 0 again. Initial instance, there is a spike in the voltage due to the presence of the reactive power that is still going to 0. So after some examples of model validation in Modelica, let's consider some aspects related to model management of a library like OpenIPSL. Several software tools have been developed over the last decades to help all the players of the electric power system sector in operating and planning of electric networks. Proprietary software tools are not flexible when attempting to share models and data between computer programs. And also dynamic simulation results between different simulations are inconsistent because of the different re-implementation of models in each simulation tool. And this led to the idea of creating a Modelica library that is the OpenIPSL to overcome such issues. And some challenges about the development of the library arise. And they are coming from project versions, model testing, and new model integration into the repository. The solution for these issues is to use the version control. That is a method of mitigating the different versions of a project that can arise when multiple parties are contributing to the same project. Another fundamental aspect is the continuous integration. The model verification part can be made automatic to reduce error margin and improve the efficiency of modeling tasks. The testing procedure automation should be triggered so the code is executed once a change has been submitted by a user. This way, every time there is a new change, the team is sure that the change has passed all the tests and will not break the project. So to provide a formal description of the steps necessary for a complete implementation of our system components, we start saying that the validation of the basic components of the OpenIPSL library has been based on 3 network templates. For each of them, 3 different types of disturbances have been considered to test the dynamic behavior of the components in different scenarios. Some guidelines about the model implementation and testing will be given in the following slides. The manual implementation and testing of the models do not quantify the discrepancies of the trajectories considered to validate the models. But then a framework for automatic testing and validation is necessary. The reference results from PSSE, this framework, have been generated using its Python APIs and saved into CSV files for each component and for each disturbance scenario. Always using Python scripts, the Modelica results from the OpenFSL library have been converted into CSV files. And then a tool called the CSV compare has been used to compare the results and verify that the trajectories are within a 1% tolerance to around the references. It is also possible with this workflow to check when a model fails, as you can see here. The tool also creates HTML reports summarizing the whole validation. So the process of implementation starts with the assignment of a model to be implemented. The identification of available technical information about the model is necessary for its implementation in Modelica. This is what I was describing here before. So if the PSSE manuals do not present sufficient information about the model's dynamics, then it is necessary to find additional literature. And once the documents describing the model have been identified, collected, and analyzed by finding the block diagrams or the equations, for example, describing the model, then it is possible to determine if the building blocks of the model are already in the OpenFSL library or not. So it might be required to implement missing blocks or functions before building the entire component model with the appropriate initializations of the subblocks. To assess the validity of the model to implement, a small test network, SMID, is used both in Modelica and the reference software that in our case is PSSE. The reference results from PSSE have to be generated. After that, the software validation can be performed. The guide slide. So after assembling the SMID in PSSE, it's necessary to obtain the steady-state computation results of a power flow, export them, and provide them as initial guess values to solve the initialization problem of the corresponding SMID in Modelica. The import of the power flow results can be made manually or automatically, increasing numerical accuracy and reducing human errors. Next, the scenario of the dynamic simulation in both tools can be defined, and the dynamic simulation of the SMID in both softwares can be run. Once the results are generated, the quantities to compare can be chosen and exported in the appropriate format to be used in another tool, for example, the CSV compare that we have seen before, that allows to quantify the discrepancies. If the errors between the quantities to compare are within the tolerance, then the validation is complete. Otherwise, more debugging of the model is required. And a better insight of the model dynamics can be obtained by comparing, for example, subcomponent inputs, outputs, states with the corresponding signals from an SMID in PSSE. The iterative process continues until the difference between the signals is below the tolerance. This process can be considered part of a continuous integration and regression methodology. So after introducing the regression testing routine, another automation procedure is necessary to verify the code, models, and library before they are committed to the GitHub repository. And the solution came from software engineering concept known as continuous integration. In this flowchart, you can see a different step of the continuous integration process. GitHub is the repository service where the Python automation code is located. CI is the manager of the pipeline, and Docker is the container service that allows to create a container that has all the libraries and dependencies for our model library and verification scripts. So every time there is a commit or a pull request, the scripts will run the following step. Build the repository and the Docker container, check the syntax, the models, run the different tests that is bus fault, load variation, and the reference step for all models, and then notify the user in the repository if all the models run successfully or not, and then allowing or not the merge. Now we can consider an application of Modelica implementations and FMI standard in the cloud. So in this section, we will see a proof of concept of model calibration in the cloud. The calibration of reactive power system models is important to ensure that the models accurately represent the behavior of the actual systems. And this process involves adjusting the parameters of the models to match observed data, in this specific case, phase of measurement units data. Power system models are used for analysis and planning studies. So it is crucial that they represent the true state of the system to avoid unexpected and sometimes catastrophic consequences. So the proof of concept workflow for the calibration of the generating unit is given in this slide. The challenge is that typical generator plan models are isolated in simulation tools and cannot be deployed in cloud platforms. So the solution that was proposed was the use of Modelica and FMI standard. With this approach, like implementing the model in Modelica and verifying it against PSSE, and then if the results are satisfactory, export the Modelica model as an FMU, and then deploy it in the platform for model calibration using some Python functionalities. So after the software-to-software validation of the model, it has been modified, the model has been modified to interface it with real measurements given as inputs. This new version of the model has been then exported as an FMU with source code to work on the calibration in the cloud platform. In order to complete the workflow, the planned model exported as an FMU has been deployed in the online platform that was called Predictive Grid, retrieving the PMU data that had to be processed before being used for the calibration of the models. The signal processing has been performed directly in the cloud using Jupyter notebooks, as you can see in this slide. Through the use of Jupyter notebooks, a specific library for connection to the platform and data retrieval has been imported. And in addition to that, the import of standard Python modules for mathematical calculations, data processing, and another tool called ModSpy for parameter estimation have been used. Once all the tools for the calibration have been set up, the FMU of the plant has been instantiated, the inputs and the outputs quantities of the FMU have been defined together with the parameters to be estimated and the algorithms and their settings for the estimation. The calibration has been carried out considering 4 parameters for this case and 2 scenarios, ambient and transient conditions. From the results, we can see that the exciter gain, Ka, keeps a value of the same order of magnitude in both scenarios, whereas the time constant, Ta, has a difference of several orders of magnitude. So the current parameters being used in the model do not represent dynamics accurately, the dynamic running of the measurements. The component models may need to be revised because the source model cannot represent the dynamics from the measurements, as we can see. Another cloud application for reactive power systems analysis is considered in this section. So we will now focus on an application of synchrophasor measurements, the possibility to perform an advanced diagnosis method for power system components using cloud-based environment that can support both real data and the simulation of models. For this case, we consider a test called Mod25 that is used to characterize the generator's capability curve, including generator's terminal limits, as well as excitation limiters. The test is performed in entire power plants with their output below a certain level. In this case, we consider a power plant composed of 3 identical synchronous generators powered by gas turbines and having hot air outlet connected to a steam turbine powering a large 4th synchronous generator. The active power output of the large generator that we call unit A was reduced to a minimum level, and with leading power factor, a large power oscillation was observed, as we can see from these plots. Much of the data used to study the oscillation comes from the transmission line receiving end, that is a substation to which the power plant unit A is connected via a 500 kV line. In order to compare the data from both sources, one is the low voltage side of the trafo of unit A, and the other source is the receiving end of the transmission line, a set of spectrograms is used. The spectrograms can be seen as a three-dimensional visualization of signals frequency content over time. And the plots denote brightest colors for highest power spectral density estimation. And spectrograms are used to identify when oscillation manifests itself and to verify in what measurement data the phenomena can be observed. So we can see in the plots on the left of this slide that a brief oscillation is observed around 1.5 Hertz here at the transmission line receiving end, but it's not visible in the spectrogram of the unit A. The same structure of the power plant unit A is used in a nearby power plant with a sister unit that we call unit B. So the idea to analyze the spectrogram of the power of the unit B, of the voltage magnitude of unit B, came out, and it was compared, as we can see here on the right, with the spectrogram again from the transmission line receiving end. And in this case, we can see how there is a bright spot here corresponding to 1.5 Hertz for the unit B, to the other bright spot for the transmission line receiving end. So now it's necessary to identify the source of the oscillation, if it's unit A or unit B. And to do that, the good tool to characterize the system underlying dynamics from the available measurements is used, and it's called power spectral density. So to find the origin of the oscillations, a comparison between the power spectral density of voltage magnitude of unit A and B is performed, as we can see in this plot. Also, the frequency domain decomposition is used, and the 1.54 Hertz oscillation mode is decomposed and its mode shape is estimated. The frequency domain decomposition provides the information on the presence of multiple oscillatory modes that could potentially have similar frequencies, like multiple modes with same frequency. This information is given by the calculation of singular values in the cross spectral density matrix. And the singular value calculation of both data sets identify only one mode at 1.54 Hertz with a higher value for unit B than for unit A. The mode shape calculation also shows a higher value for unit B compared to unit A. And finally, the normalized participation factor, if we consider it equal to 1 for unit B, then the corresponding one to unit A is 0.008. So all these results converge to the fact that unit B is the source of the observed oscillation. So now that we know that unit B is responsible for this oscillation, the first idea is to find some sort of event that triggers the oscillation. And by the use of continuous wavelet transform, it is possible to find that the nature of instability is angular, and that means it is associated with active power output from the steam unit. So we can see the plots show a comparison between the active power plot, the power output calculated from PMU data, and the spectrogram of the voltage magnitude at unit B. And the highlighted window in red shows that the oscillation around 1.54 Hertz appears as soon as the active power output of the unit drops from 600 megawatt to approximately 420. But since there is no synchronized measurements available for exciter field currents, mechanical torque, or stabilizing signals to damp oscillations, to complement the data analysis performed so far, models are necessary. And the Modelica models for power systems can be built using OpenFSR, exported as FMUs, and simulated into the cloud. The same environment where real data is analyzed via dedicated Python libraries. In order to proceed with the analysis and address the issue for understanding the mechanism that contributes to the oscillation, the Modelica model was built for the power plant unit B substation, as we can see down. The substation model has 3 gas units and a steam turbine. They are all connected to bus 2 through transformers. And a load is placed at bus 2, and it's also connected to a noise source in order to produce variations that are similar to ambient conditions. So after performing various simulations in the cloud and using different loading conditions, it was observed in the real that were observed in the real data. It was verified that depending on the loading conditions, some pairs of eigenvalues became unstable. And this is confirmed in the model as well, where we can see the unstable simulation here and a stable simulation here. So the Modelica models are equation-based, and they enable reliable linearization to be performed. The eigenvalues for the model that results in a stable simulation are presented in this slide. And as we can see, there are eigenvalues with negative damping, and they are located on the right-hand side of the plane. With the linearization of the model, we can also understand the states that are contributing to a certain oscillatory mode. And when the linearization is performed for the stable loading case, the eigenvector analysis lists the existence of poorly damped oscillatory modes of approximately 1.7 Hertz, which are a result of the interaction between excitation systems from all 4 units present at the power plant where unit B belongs. So this interaction might be what is being observed in reality, since they have similar frequencies and they are also poorly damped. So summarizing, we can say that this research work presents an evaluation of the Modelica language for modeling and simulation of electric power systems. In power systems, the modeling and simulations tasks need to be based on robust and reliable techniques, because they are used for planning and operation purposes. The implementation of models for both phasor domain and electromagnetic transit studies shows results comparable to the commonly used tools by the power industry. Modelica is adequate for the representation of power system models, presenting virtually the same results as de facto domain-specific tools. Challenges present in model management of power system library that is open source and continuously developed by community users and developers. And strategies such as version control, together with continuous integration, should be used to overcome the challenges while maintaining robustness and reliability of the developed models. The framework for the OpenIPSL library development and maintenance has been provided as proof of concept. We have seen that Modelica models can be used in cloud-based environments in order to perform calibration and power system analysis studies through the use of the FMI standard. So the results of this thesis can be seen as a proof of concept of the technologies and methods that can aid in the development of new efficient and flexible tools for grid operators. This is a list of papers and presentations with some of my contributions. Finally, I would like to thank the committee members, the current and past members of OSCE Lab, all the collaborators, companies, organizations that allowed with their funding for all this work, the CSC department, and family members and friends.
Thank you very much
for your attention.
Thank you very much, Giuseppe.
Thank you. Nice presentation.
We give you some virtual clapping for you.
Thank you.
Great. All right. I would suggest that we allow any further questions from the audience at this point before the committee, if you guys are okay with that. Yes. Is there anybody from the audience that wants to make any questions?
No, it's nice work and congratulations. Yeah.
Thank you. Thank you very much.
Yeah, no congratulations yet. He has not
Yeah,
found that.
exactly.
So congratulations for the work. Not anything else yet. Good. Okay, so if there are no questions from the audience, does the committee want to make any questions that are?
Can I ask a question?
Yeah, go ahead, Krishna. This is
Yes.
the guest.
I saw you verify the models with PSSC, but if somebody wants to modify, verify the models with some another tool.
Yes.
So since you are FMU that is set up, you have that the models. So will they just work as is, or depending upon the model in that particular software, maybe you have to tweak it and or anything like that, or you tried with different tool? What is your experience in that?
No, so I haven't tried using, let's say, exporting these models as FMU and using them in any of the standard commercial tools for power systems.
Okay.
But from my experience about the implementation of the models, I think some discrepancies might be expected, because even basic blocks can be implemented in different ways in the different tools. So the way it has been implemented, the way that these models have been implemented using PSSC as reference is kind of specific. It might work or it might not work depending on how the same models have been implemented in the other power system tools.
Okay, thank you.
Yeah, I mean, particularly the limiting PI controller in PSSC was implemented in a way that was state of the art 30 years ago or more, probably. And if you want to tool-to-tool validation, you have to do that even though you know better ways to do a limiting PID controller. That's the way things are. And that happens quite often with legacy tools. I think that shows also the advantages of using something like Modelica, where you could easily compare that to more modern implementations.
Very good. Thank you.
All right.
It's very good work, though. I mean, it's a kind of a good reference point to a lot of tools if somebody really wants to have kind of modern interface to the commercial tools, so give more freedom to the developers or anyone equipment manufacturers to develop their model. So it's really good work, I should say.
Thank you for the questions. Is there any other questions from the audience? No? Okay, I suggest then that we go to the session with the committee. So I'm going to now ask, I should stop recording too.